Okay, thank you very much. Yesterday while lecturing, you may have noticed I had this moment where I was looking at my slides and wondering, what am I talking about? But then in the evening, I went around and listened to the student discussion and found out that, of course, they had figured things out anyway. So that's the great thing about being surrounded with all these brilliant young people. An old man can stand here and say something stupid. They still make something good out of it. So that's... it's like this old European story about the traveler who arrives at a village and makes stone soup. If you don't know that story, you can read that instead of listening to my lecture. Look it up. Right. So at some point, I think what I should have done is started with this definition at some point, maybe before introducing the local system, the universal local system. That is, we discussed this category of unipotent locally constant sheaves on the étale site of X bar, which was algebraic closure, base change to algebraic closure of a curve over Q, right? And then given a point, there's a fiber function out to vector spaces instead of finite sets, like in the case of the profinite pi1. And then the unipotent fundamental group could be defined to be the tensor-compatible automorphisms of this fiber functor, similar to the case of representations of a finite group, whereas the homotopy classes of paths is given this scary definition of being the tensor-compatible isomorphisms from the fiber functor at B to the fiber functor at X. And I guess what I was proposing was that one computes this, in some sense, these definitions by using the universal object. Like the universal pointed covering spaces, either in topology or for finite coverings. So from there, I'll just remind you, there was this system, this theorem, that this category of unipotent QP local systems has a universal pointed object, meaning a projective system of local systems. Each of those E sub n's are themselves finite dimensional QP vector spaces, systems of finite dimensional QP vector spaces. And the V is a system of vectors, elements inside the fiber over B. So this is what the point is, like in the case of a pointed representation of a finite group. Right? And it's universal in the sense that if you're given any local system and a point that is an element of the fiber over B, there's a unique map from our universal thing to that pair. And again, I'll remind you briefly, the way you constructed it was by constructing this universal unipotent representation of the fundamental group based at B. And I heard yesterday people figuring out why this was the universal unipotent representation. So if you haven't done it already, you can try that now. Again, instead of listening to the lecture, you'll get something out of it that way. Anyways, then you took the limit of these things and got that E. That limit, or you can consider it as a projective system. So then you associate the locally constant sheaf via the associated bundle construction to this representation. So that was the E, and it came up with these co-multiplication maps. And then the relation to the definition of the fundamental group and the torso of path was that the endomorphisms of the fiber functor just become the fiber of the universal object over B. Right? And the proof is exactly the same as in the case of the universal covering space of a topological space, word for word almost. So any endomorphism of the functor, in particular, will act on the fiber of the universal local system over the B. Yeah, so you get a linear transformation of E sub B. But then by letting it act on the point, that vector V on the fiber, you get some other element of the fiber. And this is a bijection. And then again, by combining this together with the exactly same consideration that goes in with the case of representations of finite groups. That's why I gave those proofs so that I could skip these. Right? There's the unipotent completion. This unipotent fundamental group is in fact isomorphic to the group-like elements inside the fiber at B. Group-like in the sense of compatible with this co-multiplication, while the torso path is given by the group-like elements in the fiber at X. So that will give you the torso path from B to X. So I'll say a little bit more about this later, but there's also, it's a unipotent group, so it has this lower central series filtration such that when you go the quotient modulo the lower central series, these just become finite dimensional algebraic groups over QP. And in fact, this filtration is compatible with the filtration on the, by the powers of the augmentation ideal on the E, right? In the sense that formulated reasonably, somewhat carefully, which I'm not doing right now here, these can be also realized as a group-like elements inside E subscript N. Okay. So another way of stating this, so Dick made this comment yesterday, another way of stating this group-like property is, in fact, if you take the dual over a local system, so this linear continuous dual, that is, you take the dual of each of these finite dimensional quotient En, and now since the Zns form the projective systems, the duals will form an inductive system, and you take the inductive limit, then this becomes a sheaf of QP algebras by the dual of the co-multiplication. It's in fact a commutative sheaf of QP algebras. And if you look at that group-like property that stated via the original delta, in fact, it ends up, this U ends up just being the spectrum of this algebra over B, whereas the torsor of paths become the spectrum of the fiber over X of this dual algebra. So that's just a translation, in fact, of the group-like property. So in other words, the algebra homomorphisms from here to QP. Okay, so remember, what we're actually interested in is how this thing varies with X. That's why one needs to go through this unipotent universal local system a little bit, or at least some object of that sort, because we're not just interested in what happens at B, we want to see what happens when we vary X. So to give something like a slightly more concrete description, this is also very hard to use. I'll make a remark on exactly how it's varying, at least from a co-cycle point of view. So how does one do this? Well, this P, this torsor of paths, remember, it's a subspace, or well, it's actually a subscheme of E sub X, sub-pro scheme of E sub X, given by the group-like element. So if you want to understand how the Galois group acts on that thing, remember in this context, in the état context, we're interested in Galois action on all of these objects. How does it act? Well, the action on that thing is induced by the action on the fiber of the universal local system itself, so we need to figure that out. But how does that act? Well, you see, remember, the E, the fiber over B, or the universal representation we started out with, that's acted on by the fundamental group by a kind of quotient of the regular representation, right? It's a completed group algebra of pi 1, so everything is just, the pi 1 is just acting by left multiplication on E. Right? But then remember also that the fiber of the universal covering space at X is a twisted form, it's a torsor for the fundamental group based at B. Right? So, in other words, we know how the Galois group, in some sense, acts on that fiber, and that's the action that tells you how to twist the action on E to get the action on the fiber over X. So, described in terms of co-cycles, the action on that torsor of paths for the profinite fundamental group, that's what the fiber over X is, will be given by a co-cycle of the Galois group, but then you twist the action on E using that co-cycle via this formula. So this is the original action on E, and then you twist it by the co-cycle given by that fiber over X of the universal covering space. So this is one slightly more concrete way of thinking about how the action is varying. It's how this co-cycle varies as you move over the different X's. But of course, the idea is that in spite of the fact that I'm giving it this description, understanding the action on the fibers of this universal unipotent local system is actually easier than understanding the action on this universal covering space. This is actually harder. And so this linearized action should be easier. It's still hard, and we're still struggling to understand it in any given instance, right? But this is one way of thinking about it. Now, regarding these generalities about the unipotent fundamental group, maybe I'll just make a few more structural comments. Again, which I think many people had already figured out yesterday when I listened to the discussion in the evening. So if you look at the map that sends G to G, the class of G minus 1, this induces an isomorphism from the abelianization of the fundamental group tensor QP. So that is the Drum homology, first Drum homology of the curve, to the augmentation ideal modulo I mod I square. So this is an isomorphism. So this kind of thing works for completion of any groups. So, and it's a relatively easy exercise. But here, what we're saying is that this isomorphism occurs compatibly with the Galois action. So we get this I mod I square, you can just think of it as the Drum homology of X. Now, by the way, it's not as though the Drum homology of X, which is the QP Tate module of the Jacobian, it's not as though that's easy either. That's already hard. We already know those Galois representations are very hard to understand. But we're souping it up, of course, further. Well, those are hard, but at least people have worked on those for now 60 years or so. So we feel like we know what the difficulties are, and then we're trying to use that to move further to these unipotent completion. Of course, there's a multiplication map, an n multilinear multiplication map that is from nth tensor power of I mod I squared to this I to the n mod I to the n plus 1. And now this gives us a description of this piece. And how does that description go? Again, remember, this is just a homology according to that first line. So this map will be surjective on the one hand, and it will induce an isomorphism from the nth tensor product of the homology modulo some subspace to this, this level of the filtration by the augmentation idea. So what is that thing? What is that K? So I need to describe that for you. Again, we can pretend that we understand this tensor product since we understand H1, right? Although it's still hard. Now, but then we have to take this quotient. What is this quotient? Well, the quotient Kn, one description is as follows. First of all, I'll introduce some notation. We denote that quotient by T subscript n. I don't think I've ever used this notation consistently, but I'll do it here. I'll introduce one here anyway. So that is actually the dual of something that I've written as R superscript n. So R superscript n is a subspace, therefore, of H, the cohomology, first cohomology to the nth power. So these and these are dual, right? And this Rn is just the annihilator of Kn. So I'm going the other way around, of course. I'm going to define for you what this Rn is, right? And then Kn will be the annihilator inside H subscript 1. Right? You take quotient modulo that annihilator, and that gives you this augmentation, this piece of the filtration. Right? So I hope this made sense. And now I have to define for you what this Rn is, right? So this Rn is obtained from cup product. That's the general slogan here. How do you do this? Well, R0, first of all, is just QP. So I'm going to define this inductively. And R1 is just H1. Okay? And R2, this is the first non-trivial case, interesting case. It really is just the kernel of the cup product from H1 tensor H1 to H2. So that's a subspace of H1 tensor H1, right? And Rn plus 1 is going to be inductively defined as a subspace as R to the n tensor H1. Yeah? So for example, remember R1, well, okay, so R0 was QP, so R1 will be a subspace of QP tensor H1, and it's the whole thing at that level, right? And then R2 will be a subspace of R1 tensor H1. R1 was all of H1, so that's a subspace of H1 tensor H1 given by the kernel of the cup product. So that's how we're starting it. Then inductively, how does this go? Well, remember, Rn minus 1 will be a, so am I doing this correctly? Yeah, okay. So having defined Rn minus 1, I hope I'm going in the right direction. Yeah, so that's okay. So then you tensor with H1 tensor H1, so then there's a cup product going in this direction, right? So identity tensor the cup product on H1 tensor H1. And then Rn tensor H1 is the subspace of, am I doing this right? Yeah, sorry, I'm getting a bit confused again. Oh, yeah. So, okay, sorry. I'm assuming that we already have Rn minus 1 and Rn, and I'm trying to define Rn plus 1. Yeah? Okay, so Rn is a subspace of this piece over here already, right? By inductively. Yeah. So we get this inclusion, so then you have this composed map, and Rn plus 1 is the kernel of that. Okay, so that's the inductive definition. That's a little bit confusing, but you'll see that the indices work out, the superscripts work out. Okay, so that's the definition of Rn. So what is all this about? So I was going to skip the next slide, but I think I will explain it a little bit to give you a sense of why one goes through a definition like this. It's because this allows you to give a different kind of tautological construction of this universal object. Yeah? So I think I first read this in a paper of Halting's. I don't know if he was the first person to do it or not. I think that we wrote it out rather clearly. Together with Andrea Tajani-Ovita afterwards, many years afterwards. So how does this go? Where do these definitions come from? Well, so here's the idea. Suppose you look at the extension as sheaves from the constant sheaf QP to the constant sheaf H1. So that's the first extension, right? But then since that's a constant sheaf, we can pull that out of the X, right? So what you get is X1 of QP by QP tensor with H subscript 1. Well, tensor the homology, right? But X1 of QP by QP is the cohomology. So you get the first isomorphism just by pulling out that H1. So that's H1 superscript 1 tensor H subscript 1. But then, since these are in duality, that's just a hom from H1 to H1. So inside this space at the end, you get the identity map that corresponds to an extension over there. Yeah? So in other words, to the tautological element, identity, there's an extension like this. And that's our E1, extension of QP by the homology. Exists simply via this tautological isomorphisms, computing the extensions. Right. Now, then starting with this thing, I'll just tell you how to build up the next level, and then leave the rest as exercise. So how do you build up the next level? Well, you start with this sequence and apply hom to it. So I'm going to leave out the first term, this hom of QP, hom of E1. And then the third term will be hom of H subscript 1 to QP, right? Then the next goes over to X. X of QP by QP, then X of E1 by QP, and X of H1 by QP, then X2 of QP by QP. So this is just a long exact sequence for extensions of sheaves on X bar. Well, but you see, if you look at this part, this is just a map from cohomology to cohomology, H1 to H1 cohomology. Yeah, these are both the same. And that ends up being an isomorphism. So actually, maybe I should have tried to put this all on one slide, but look at it anyway. So what happens is that this actually turns into this diagram, this row. Yeah? So having shown you that, let's go briefly back. So these are 5 terms, right? So what I'm saying is these are the same 5 terms, because this is H superscript 1, this is also H superscript 1, right? And what is this? This is the X1, this is an X1 of E1 by QP, so then it will have an image here, right? So this one, you pull the H1 over to this side and it turns into H1 dual, yeah, which is the cohomology, H superscript 1, and then it's constant, so you pull it out. So then this term becomes cohomology H1 tensor itself. And this is H2. Okay, I hope this made sense. So these are these 5 terms. And if we move back to the same slide, so it's there again. Okay, now that first delta there ends up being an isomorphism. It might even be the identity with the suitable identification, but I'll struggle to really explain that, so just say it's an isomorphism. So in fact, that X1, this X1 from E1 to QP becomes isomorphic to the kernel of the cup product. So that's the upshot of this diagram. So in other words, this X1 is, according to our previous notation, this is our R2. The kernel of the product, cup product H1 tensor H1, which is the dual of T2 by definition. Okay? So then, X1 of E1 by T2, just if you pull out the T2 again, that just becomes hom from T2 to T2. So you have the identity element here, which corresponds to an extension like this. That's E2. So this is the tautological way of building up this object, this sheaf. And so I'm not going to prove to you for you, so it's on the next slide, a sketch of why these kind of things will give you the universal property. Yeah. So somehow, of course, if you look at the construction and you have a categorical mind of some sort, right? Yeah. Then you might suspect, gosh, something this tautological must be universal, and that's correct. Yeah. So, yeah, but I won't explain that more. But the nice thing about this description of the universal object, this works for any cohomology theory. You can see that this kind of thing, you can, using exactly the same idea, you can build up the universal local system in drum cohomology, universal bundle with connection, for example. You can build up the universal crystal corresponding to crystalline fundamental group. Any reasonable cohomology theory you want, a vague cohomology theory, you build up universal unipotent local systems inside appropriate to that category through this construction using exactly the same idea as long as you have the theory of cohomology and cup products. So that's why this is a nice construction to keep in mind. Okay, so then I'll move. So now I've caught up from where I should have been yesterday. So we'll move to the next lecture. Even though the title indicates that I'm still behind. Okay. So now let's move to the drum picture. I hope I've given some sense of this étale unipotent completion. So here, the drum unipotent fundamental group exists over any field of characteristic 0, right? But I'm going to do it over a finite extension of QP because this is the case we're mostly interested in. And later on, we'll refer to the special fiber of a nice model of X in order to discuss a certain crystalline structure, Frobenius structure coming from comparison to a crystalline fundamental group. Okay, so how does this work? So it's the same setting. There's this curve and rational points that we view as geometric points and so on. So here, the relevant category is the category of unipotent vector bundles with flat connections. And fiber functors, which just take fibers of the corresponding vector bundle, underlying vector bundle. And the objects of interest, the drum fundamental group, is still the tensor-compatible automorphisms of this fiber functor, whereas the torsor of Casa consists of the tensor-compatible isomorphisms from the fiber functor at B to the fiber functor at X. Of course, what I'm not doing here is giving you this careful exposition of what kind of category it is, right? So the buzzword is that this is a Tanakian category, which has tensor products, duals, with a bunch of compatibility properties between all these constructions, all these operations. And that's what allows us to make sense of all these notions. And then there's a general nonsense that tells you that this becomes an algebraic group, pro-algebraic group, and this becomes a scheme that's a torsor for that pro-algebraic group. But again, I'll say something about another way of understanding this. So here I'll be very sketchy because that's why I did the last few slides of this étale case. You can give a completely tautological construction of the universal unipotent connection in this setting in exactly the same way as the étale case. Namely, if you take the xi inside the category of universal unipotent local bundles with connection, right? Between two connections like that, V nabla and V dash nabla dash, then in fact you can view that as the hypercohomology HI dram of this tensor product, where the HI dram means you take, well, I guess I've defined it here. It's the hypercohomology of this complex. So there's a cohomological way of computing those X anyways, as exactly as in the étale case. So you build up a bundle with connection tautologically using exactly the same construction in the étale case. That's why I stressed that, with the fact that you can do this. And as before, this T subscript n will be a quotient of the dual of the first drum cohomology. exactly again as in the et al. Case. Quotient defined by being the annihilator of something inside the nth tensor product of cohomology. Okay. So I won't give you any more details about that, but the fact, except just stating the fact. Now, you can choose some element inside there. I'm not going to tell you how to choose one at the moment, but you can choose anything you want. Yeah. You can choose any element inside the fiber over B, yeah, of this object that we built up, right? Then it has the universal property. That is, given any unipotent local system on X, unipotent bundle with connection on X, together with the fiber of the corresponding vector bundle over V, there is a unique morphism of bundles with connection from R object to that pair that takes 1 to V. So that's the statement, which works the same way as in the et al. Case. And again, we're just repeating a bunch of statements from the et al. Case. The endomorphisms of the fiber functor will be the fiber of the universal object at P. That's why I guess I am just repeating myself many times, but that's why I kept emphasizing this universal object, because that gives you a way of uniformly understanding all these terrible endomorphisms of functors and automorphisms of functors, following exactly the same formulas in every given instance. So it works exactly the same way again, and all the proofs work the same way once you have the universal property. And again, the pro-algebraic group, the Durand fundamental group defined as the tensor-compatible automorphism, is isomorphic to the group-like elements in the fiber of E at B. I guess I forgot to define the co-multiplication. You know? Well, here it is. Yeah, sorry, I did define it. So there's a co-multiplication, again, you can view it as just coming from the universal property, right? Because this is a bundle of the right sort that admits a unique map from that thing that takes base points to base points. So that's the co-multiplication. Using that, you can prove that the Durand fundamental group is isomorphic to the group-like elements, whereas the torsor path, again, is the group-like element in the fiber over X. And as before, if you take duals, you can realize the Durand fundamental group as well as the torsor path as being the spec of the commutative algebra you get by dualizing. In the Durand case, by the way, there's one of the subtleties surrounding the Durand case. In some sense, it's easier than the et al. Case. Actually, it is in all senses easier once I'm used to it. But the subtleties at the beginning is that when you're considering the et al. Fundamental groups, you can in some sense always rely on the topological fundamental group. There's a topological fundamental group over C, for example, whose completions of various sort will always be isomorphic to the target object that you're interested in. You should take two table completions of topological fundamental group. That's a concrete way of thinking about QP unipotent completion of the theta fundamental group. These are all isomorphic. So there's a kind of well-known object that we can use as a starting point. But if you're considering the Durand fundamental group over a field like QP, there's no such underlying object. You just have to start from the beginning. And build up your group. And then this kind of tautological construction of the universal object is useful. Now, so we're moving to a part which I recommend that you black box for now. And if you get confused about anything about this Hodge filtration, which is a bit subtle, so there's somebody in the audience you can ask. So I always ask him anyway. So this universal bundle width connection has a unique decreasing filtration that's called the Hodge filtration with the following properties. Right? So again, decreasing means that F0 contains F1, contains F2, and so on. You know? So these are subbundles. And they're not subconnections, they're not preserved by the connection, but nabla applied to Fi anyways is contained in Fi minus 1. So at most it gets one step bigger when you apply the connection. Now, but remember, this bundle comes with filtration by these constant bundles with connection, just given by parts of cohomology. So this Tn is a quotient of H F1, the Ram homology, right? So that has a natural Hodge filtration just coming from ordinary Hodge theory, right, and cohomology. So this filtration Fi should induce on these constant subquotients the usual cohomology, the usual Hodge filtration coming from usual Hodge theory. So that's the second property. And the third property is that our base point 1 should lie inside F0 at the fiber. So with these three conditions, there ends up, you can prove that there's a unique filtration with these three properties. It is kind of convenient because it's hard to compute this Hodge filtration. I don't know about real experts. For me, it's very hard to really see how these Hodge filtrations are varying with the points. But using this uniqueness, sometimes you can just compute it. Given a suitable presentation of the bundle, uniqueness of a filtration with this property allows you to see how it varies over the points. So there are some papers on this subject that I've put in the references. But anyways, so that's the Hodge filtration. So this induces a Hodge filtration on the dual. So the Hodge filtration on E ends up having, I guess, which way did I do it? Non-positive degrees, right? Essentially because the Ram homology H1 has non-positive degrees in the Hodge filtration. And if you dualize it, you get a filtration with non-negative degrees. So the largest part is F0, and the next part is F1, and so on, right? And that F1 ends up being an ideal. Yeah? And so you can use that to define a subscheme of this torsor of paths as being defined by to be the zero set of that F1. And what I won't prove is in the next slide, if you're interested in looking at the proof. This F0 ends up being a torsor for F0 of U. So for U itself, this F0 is also a subgroup. I think I wrote, by the way, maybe this is a good place to insert an erratum. In one of my papers, I made some mistake stating that Fi's are also subgroups. None of them are subgroups except for F0, and that's the only one we need. So for U itself, this F0 is a subgroup, and it acts on this F0 of all these torsors and turns it into a torsor for this subgroup. So the sketch of proof for that is on these two slides, but I'll skip that. Okay, so what have I done? On this, we've defined this U, we've defined these P's, torsors of paths, and discussed very sketchily the fact that these come with Hodge filtrations. With these natural filtration. Now, there's one other structure, which is the crystalline structure. So here, again, I'll give you a working man's definition, or working person's definition, sorry, of how this works. Yeah? And then, as in the Hodge filtration case, there are experts who can answer your question. I can't really answer your questions about this. I sort of struggle my way through it, but still tend to black box a lot of the properties. But Kiran and Jennifer and Evan, they can all answer concrete questions about how this works. Okay, but here's a description. So the point is that the category of unipotent bundles with connection, yeah? So the fancy way of saying it is that, so there was this integral model that I introduced at the beginning, the script x, right? The German x or whatever that x is, x, whatever. So there's that script x, right? That was the integral model over zp, right? And so the slogan is that if you take the reduction mod p, that was the y, that's a scheme of characteristic p, but the isocrystals on y is the category of this thing called isocrystal. So that thing that's intrinsic to Y is the same as connections on the generic fiber on the original X that we started up with. So that's the slogan. Somehow, the category of connections that we started out with only depends on the special fiber. Now, if this is open thing, then you have to say various things about convergence and so on. But anyways, the statement itself is basically correct. So what this means is that, so if you translate this into the part that's relevant for us, it means that the Frobenius morphism of the special fiber actually acts on the category of connections. For these unipotent connections, these all end up being so-called over-convergent isocrystals. And that's actually somewhat important for this integration process. So, but how does this action work? Well, we cover our scheme X by open subsets with the property that each UI is a smooth lift of its reduction mod P. So you cover it by liftings of characteristic P schemes. And then the characteristic P has this Frobenius map that you can at least locally lift to characteristic 0. Now, given a bundle with connection, then its restriction to each of these UIs, you can pull back with this local lift of Frobenius. And the magical part is that these all glue together to give a global pullback. You can use the connection itself to glue these different ways of pulling back over the overlaps. There's a canonical isomorphism between these two things that give you the global pullback. So as I said, if you accept that magical part, that there's a natural gluing over the overlaps, this is how you define the Frobenius pullback of connections. And as I said, you can ask the actual experts how this works. So in particular, we can take our universal thing, right, and pull that all back. But then because it's universal, there's a map from here to here, which gives us the Frobenius action on the fiber over a QP rational, but a QP rational point will not move under the Frobenius. So it acts on the fibers over any rational point, QP rational point. So you get this Frobenius action on all of these objects. So that's the construction, or a brief sketch of the construction. Right. Now, an important fact is that, remember, there's these constant parts coming from tensor product of duals of cohomology, right? Yeah. So there, you have the Frobenius action coming from the fact that the drum cohomology of X is isomorphic to the QP coefficient crystalline cohomology of Y. So this is an old isomorphism, comparison isomorphism between crystalline cohomology and drum cohomology. And the Frobenius action, just defined in a slightly elaborate way, actually agrees with the Frobenius action on the usual crystalline Frobenius actions. And furthermore, so by this general nonsense that used to be regarded as mysterious, maybe it's still mysterious, but anyways, many people know it at this point, the way the Frobenius acts on various Weil cohomologies are compatible. That is, the eigenvalues are all the same, no matter which way cohomology you act on. In particular, it is the same as Frobenius action on the tau cohomology. A consequence is that, in fact, inside this torsor of paths, there's a unique Frobenius invariant element that follows from this statement. So how does that follow? This is a very elementary fact, but it appears there have been quite a few questions about it, so I'll tell you how it goes. So there's this thing called the Lang map on this unipotent fundamental graph. What does it do? It sends an element U to U phi inverse U. So it's somehow using the Frobenius and combining, oh, sorry, I think I wrote something wrong. Phi U inverse, sorry, not phi inverse U, phi U inverse. No, phi of U inverse, right. But that's actually a bijection. And identity, in fact, is the only element that's fixed by phi. And the reason is obvious. It's because when you restrict it to this associated graded quotients, right? Oh, sorry, this is a slight mistake. This is a subspace of that. It's not the whole thing. Remember, that Tn was inside the universal thing, and this associated graded quotient of the U itself is a subspace of that. But it doesn't matter, because in any case, on those subspaces, the eigenvalues of 1 are all different, or phi are all different from 1 by the Weil conjecture for curves. The Riemann hypothesis for curves. The way phi acts on H1, H superscript 1 has weight 1. So on all of these H to the n, it has weight n, and then it becomes minus n when you dualize. So there's never an eigenvalue 1 that occurs inside its action on these graded quotients. So in fact, on this graded quotient, it's an isomorphism, and then by 5 lemma or something, it's an isomorphism on all of these UNs. So that's the key point. So now if you want to prove that there's a unique Frobenius invariant path inside any of these torsors, right? It doesn't have to be these past torsors, in fact. So as a consequence, for any torsor for U with a compatible action of phi, there's a unique Frobenius invariant element. Why is that? Well, you choose any element you want inside your torsor, right? then if you apply phi to it, because it's a principal bundle for U, it's related to the original point by some U, right? But that U, according to the lemma, can be written as V phi V inverse for a unique V. So then, what does that equation say? It says that phi P equals P times V times phi V inverse, but then you get this, right? Okay? So you get a Frobenius invariant element inside the torso. And the uniqueness I'll leave to you. So that's the Frobenius invariant. So there's actually a description. So this is actually also computationally important. So I'll say it. I'll describe it in some detail. You don't have to know what it is, because I've already more or less said what it is. But without giving a formal definition, there is a notion of a crystalline fundamental group, right? Which you can think of as being defined in the same category as that we've already just described for the Durand fundamental group. It's just unipotent bundle with connection. That's what the category is, right? But we changed the fiber functor. It's because this category that we're interested in, isocrystals, is the same as this category of bundles, but the fiber functor is different. What is the fiber functor? Well, first of all, the point we're interested in is a point on the special fiber, and that's what defines the fiber functor in this for the crystalline fundamental group. And the functor, instead of associating of a literal fiber, what it does is it restricts your bundle with connection to the tube of Y. I guess people have discussed tube enough now that this is a familiar notion. And that considers horizontal sections of the bundle on the tube. So what needs to be shown, of course, is this has, if V is of rank n, our unipotent conditions imply the convergence conditions, etc., so that in fact on any of these tubes you have n linearly independent sections. So this is a vector space of dimension n for any y. And so you get a fiber functor of the right sort on bundles with connection by looking at tubes. Now, so then suppose you're given 2 points in the tube. This is this discussion of small, tiny integrals, right? Which is that, so how do you get, remember Frobenius invariant path, whatever it is, it's supposed to give you a canonical way, canonical isomorphism between the fiber of any unipotent local system at X to the fiber of the local system at X dash. That's what it's supposed to do. That's what a path is in this context, remember, because it's an isomorphism from the fiber functor at X to the fiber functor at X dash. That's a path from X to X dash. Yeah? So how do you get that? Well, you take a vector in here and find a horizontal section with that initial value. Right? And then you take that horizontal section and evaluate at X dash. So that's the isomorphism. So in other words, it's by solving the differential equation, yeah, and analytically continuing. Yeah. Well, it's a small continuation in this case. From this point, initial condition, solve the equation and evaluate at the other point. So that's the fiber functor. So why is this the Frobenius invariant? So you have to think about that a little bit, right? And I'm probably not going to say it correctly, but essentially, so I'll try to say the right keywords that tell you why this is correct. So this construction that I gave you just now, if you apply it to every bundle, right? This is compatible with the Frobenius action. So that's one way of saying why this is the Frobenius invariant path. This construction is compatible with pullback by Frobenius. And so that's what the Frobenius invariant means. So those are the tiny integrals. Well, I say integrals. Okay, so I'll say a bit more about how this relates to actual integration. But so far, to use the right terminology, this is the holonomy, the tiny holonomy. Along some path, this canonical path from Vx to Vx dash. So from the theory of connection over the complex numbers, you know that if you pick a path from one point to another, there's a holonomy isomorphism from the fiber over one point to the fiber over the other point. So this is the holonomy. Right? And integrals typically appear as components of that holonomy. So the integrals are underlying this discussion, but the correct terminology here is this is the tiny holonomy of the connection along some canonical path. And then there's a way of relating different tubes. So this is the theory, the proper theory of Coleman integration. And how to compute this, of course, is am I correct to say that this is Kiran's theory, and Jennifer and a lot of other people, I'm not sort of giving the proper attribution, but actual computation of this, of course, these experts have really developed. But we know that there exists such a thing. That's what we just proved. The existence of this isomorphism is the existence of this Frobenius invariant path. Right. Now, okay, so this is a bit of a complicated slide, so I'm going to tell you, don't read it, I'll just tell you what it says. So the point is that whenever you take one of these torsors, right, torsor of paths from B to X, let's say, right, for the drum fundamental growth, it has two trivializations. One is this canonical Frobenius invariant path that gives you one element. But another element is you take an element inside this F naught. That's the Hodge theoretic trivialization. So there's an element inside F naught that you regard as a Hodge trivialization and the Frobenius trivialization. And the difference between the two defines an element in here. So this is the way you assign an element to this homogeneous space. You should think of this as being like a p-adic period domain of a very simple sort. It associates to a torsor an element in here by trivializing it in two ways. One, the Frobenius invariant path, the other, the element of F naught. Then you can think about various period map in usual Hodge theory of the complex numbers also in exactly the same way. There are often two trivializations. One, for example, in usual Hodge theory, there's an integral trivialization and a Hodge theoretic trivialization, one compatible with the Hodge filtration, one compatible with the integral structure, and then you get an element in a homogeneous space like this, very similar in nature, except because there's this integral lattice, it's usually a quotient or something like this, so it's more like a locally symmetric space when you do it over the complex numbers. Here, because there's this canonical path, no ambiguity exists, so the only ambiguity is in the Hodge theoretic part. So this thing classifies torsors for the drum fundamental group together with these two structures, Hodge filtration and the Frobenius section. Okay, I'm going to give a rather explicit description of this process for the case of affine curve. I think when did I start? I started past 11:10 anyways. I think I was looking at this. So I think I still have a bit of time. Sorry?
Until about 11. So 5 or 6
Sorry?
minutes. You give about 5 or 6 more minutes.
Oh, okay, yes. Okay. I'll do my best to reach a satisfactory point. Satisfactory for me, I don't know for you. But okay, so here's a kind of explicit description for affine curves. Then to modify this for projective curve actually is not so easy. But anyways, let's choose a set of global algebraic differential forms representing a basis for drum cohomology. So M will be given by that formula related to the genus and the number of missing points. Now consider an algebra generated by just these symbols. Now big A1, big A2, etc. up to AM. So this is just a tensor algebra of the F vector space generated by the AI. That's what I mean by this. It's a non-commutative algebra, the tensor algebra. Now, this has this natural co-multiplication, and we can build up a completed version of it, right, in this way by taking quotients modulo the augmentation idea. Yeah, so then you have a co-multiplication on that as well. Now I'm going to define explicitly a pro-unipotent vector bundle with connection. Namely, just take this E here, right? Or if you don't like the completion description, just take every finite level and then tensor it simply with OX. It's just a trivial bundle, in other words, right? Except the underlying vector space is E. And on that, we define a connection by this formula. So what is a section of this bundle? It's just a function from X to E, right? So you take a function and take d of it minus that gadget over here. So remember, those alpha i's are differential forms, right? And that ai fi is another element of E. So this gives you a map from the section E tensor OX to E tensor omega 1. So that's what this is. So that's the connection. and you just take the element, I think on element of the way I said it, 1 probably makes sense. I'm a little bit confused now, but I am. Yeah, the 1 which and the constant part, that's the 1, yeah, in the constant part of the group algebra. Okay. Then the theorem is that this actually is the universal unipotent bundle-width connection. This has all the properties. So in order to do that, we just have to show that it has the right properties. Yeah. But this is an explicit construction of the universal unipotent bundle-width connection in this case. So how does this work? So I won't prove this lemma. It's a fun exercise. And if you get stuck, you can look at the papers given in one of the papers, my paper on unipotent Albanese map. And so the point is this, that if you're given any unipotent bundle-width connection on an affine curve, then you can write it in this form. It becomes isomorphic to the trivial bundle. The fact that it's trivial is clear because you see it has to be a repeated extension of trivial bundles, and on an affine curve all these extensions split. So it has to be a trivial bundle. And the connection has to look like this. Is D plus these alpha was a choice of differential forms at the beginning times some nilpotent matrix like this. They are all of this form. So if you use this fact, it shouldn't be hard to imagine that given any such things, there's a morphism, a map of connection from our universal object, or putative universal object to this thing. So that's how you prove it. So that's the basic thing. Now, so back to this Frobenius invariant path. So this, as we said, is constructed by taking an element of the fiber, solving the differential equation, and evaluating at some other point, right? This is the Frobenius invariant path. So how do we construct it? Well, locally, it's like this. We need to find flat sections, right? That's what that middle thing is. We have to find flat sections of this bundle over tubes. So what do we do? Well, a general section looks like this. Remember, this was the fibers of E were this tensor algebras over the AIs, right? So you can represent them as linear combination of words in the AI. Right? So a section looks like this. It's a sum over words of function coefficients and words in the AI. Well, the flatness condition, if you look at the definition of our connection, is actually this equation down here. The fact that it's annihilated by the connection is that D of F is exactly this combination obtained from augmenting with the AIs and multiplying by the form. So that's the flatness condition. So if you examine that specifically, this is what it looks like. For every AI and every word, you get an equation like this. Well, what does that mean? The point is you can solve that iteratively. So for example, for F sub AI, if you just have a word with one letter, right, then you start from the empty word where this F0, I guess I should have said something. Okay, I'm getting confused by what that is. F0 is probably, yeah. So I'm doing this just for the initial condition 1. Okay, so then F0 is 1. And then you integrate alpha I. So that's what the differential equation says. So just locally integrate, find an antiderivative of alpha I with initial condition 1 at P. So you get an integral of this sort as F sub AI for a length, for a word of length 1. Yeah, so this is, right. But all of these, remember, okay, so this is where I got a bit confused a moment. All of these guys will have initial condition 0 because remember, the section is supposed to be just 1 at the origin. So all the other components have to be 0. So then, in order to build up this one, what do? You solve that equation again with Fi times alpha j. So it's an integral of this sort. So this is what an iterated integral is. You find an antiderivative, multiply by the differential form again, integrate again, and so on. So this is how iterated integrals naturally arise when you try to find horizontal sections for this universal bundle. Okay, so then having solved the equation with initial condition 1, you can get this Frobenius invariant path for any other initial condition by just multiplying this condition, the solution for 1 onto vectors. And then, so this is what it is. So you can solve this. So the statement that I made just now is actually true in an appropriate sense for any base point B and X. But concretely, you're taking antiderivatives on a tube. But for general X, you can define the iterated integral to be the component of this element. So that's a conceptual approach. It's not you have to turn that into a computational tool, but a conceptual approach to the iterated integral is that now between any 2 points, not necessarily in the same tube, you still have this Frobenius invariant path. And you just define its component to be the iterated integral. Then it has all these nice properties simply from various tautological aspects of this construction. Then the uniqueness of this Frobenius invariant path essentially gives you all kinds of identity between these integrals that you expect from usual complex situation. So maybe another way of saying it, I'll just summarize what I said just now, is that if you look at the dual of our previous E, right? So this is the coordinate ring of the unipotent fundamental group and the torsor of path. Now remember, dualizing gives you the coordinate ring. Well, but it really is just a continuous linear dual. So this will be generated by dual basis for the W's, right, for the words. So you get this basis of functions indexed by words again. And the algebra structure ends up being given by the shuffled product. So that's the natural algebra structure you just get by dualizing the coproduct. And the iterated integral identity is saying that these things that you get, this Frobenius invariant path, is actually an algebra homomorphism from this algebra to the base field. So that's the spec of this algebra business. So yeah, I guess, sorry, I'm over time, sorry. I'll finish up with this theorem. Which says that, in fact, so if you look at the map from points, local points in a local field, to this classifying space for torsors, this period domain. What is this map? Maybe I didn't write this down properly. That associates to any point x the torsor of Duran paths from B to x. That's what this map is. And each such thing defines an element inside this period domain. So this has the property that it's the image of any tube on X is in fact Zariski dense. And it is going to be quite important because, of course, you want to take an algebraic function on that thing and show that you get a very non-trivial analytic function on the points. And this Zariski denseness is important. And the point is that now, this, if you look at it with respect to the lower central series filtration, as you keep increasing n, you get more and more analytic function. In fact, all the analytic functions as you go up the different levels, these are all algebraically independent from each other. So you get very strongly new functions as you go up the n that we can try to use to annihilate points and refine more and more the locus of global points inside the local points. So that's the idea. Okay? Okay, maybe this is a good place to stop. Yes, thank you.
Questions? Okay. Let's thank Minhyong again. We'll resume at 11:30.
So I was trying to understand what you told me yesterday. I mean, you did it here, but then during your lecture, I figured it out. I had another